In this video, we're going to talk about real zeros of a polynomial function, or at least some of the basic information that you'll need in order to find the real zeros of a polynomial function, which includes some theorems. First, we're going to revisit a topic that we've already discussed in a previous video, which is synthetic division. So I'm going to take this function x cubed minus 4x squared minus 5 and divide it by x minus 3. Now remember, when we do this, we take this constant and we look at the opposite of that constant, which happens to be positive 3, and then we write down all the coefficients of the function, in this case a polynomial. So 1 would be negative 4. Now notice here how there is it skips a term. So this is a cubic term, this is a quadratic term. There's no linear term, which means we still need to represent that with a 0. We got to have a placeholder there for it. So in other words, it's like having a plus 0x in the polynomial. We don't write that, of course, because 0 times x is 0, but it is there. And then we have the negative 5 as your constant. We write a horizontal line here, leaving some space. I put a little plus sign out here. You're going to drop the first number, which is a 1. Then you're going to take the 3 times the 1 to get a 3. You're then going to go ahead and add these vertically. So it'll be negative 1. Again, go ahead and multiply diagonally. So 3 times negative 1 is negative 3. Again, add, you get negative 3. Multiply, you get negative 9. And add again, you get negative 14. So that's just revisiting synthetic division. Now, if you recall, what this would result with is a function that was 1x squared minus 1x minus 3 with a remainder of negative 14. You could also write the remainder as negative 14 over x minus 3. And if you did that, you would put a plus after the negative 3. So in other words, it would look like this. 1x squared minus x minus 3 plus negative 14 over x minus 3. This brings us to our first theorem. It's called the remainder theorem. It says let f be a polynomial function if f of x is divided by x minus c, then the remainder is f of c. Let's take our previous problem and just kind of experiment with this, since we already have divided and we already know the remainder of the previous problem that we did. So remember, the function was f of x is equal to x cubed minus 4x squared minus 5, and we're dividing that by x minus 3. Okay, now look up here, I want to highlight something. Notice how this is x minus c, but the number you substitute into the function is c. So in other words, this is a minus. It's always a minus in this binomial right here. And so you're going to look at c as being positive when it's x minus that value. So in other words, the number that I'm going to substitute for for x in my function f of x is not going to be negative 3, it's actually going to be positive 3, similarly to what we did with synthetic division. So I'm going to put in a positive 3 here. I'm going to substitute it everywhere I see x. And the idea here is that when we evaluate this function, do our order of operations, we should in fact get negative 14, which we know is the remainder. So 3 cubed is 27. Minus 4 times 3 squared is 9, times 4 is 36, minus 5. Well, 27 minus 36 minus 5 is in fact negative 14, so it does work. So instead of doing synthetic division to determine the remainder, we can simply evaluate at that constant c, and that will determine what the remainder happens to be. Let's practice this with 2 additional problems. So down here I have f of x equals 4x cubed minus 3x squared minus 8x plus 4, and so in other words, we want to find the remainder when f of x is divided by x minus c. In this case, x minus c is x minus 2. So we are going to evaluate the function f of x at 2. So remember, you're looking at 2 in this case. And so we substitute the 2 everywhere we see x. And do order of operations. So 2 cubed is 8. 8 times 4 is 32. minus 3 times 2, I forgot to square it up here, so 3 times 2 squared is 4, 4 times 3 is 12, minus 16 plus 4, and this, when you combine all these terms, you do in fact get 8. All right, let's do number 2. Again, we're going to substitute for x. We are now looking at, this is x plus 4, which really means this is x minus a negative 4. So I will be substituting in a negative 4 for my x. So it'll be negative 4 to the 6th minus 16 times negative 4 to the 4th plus negative 4 squared minus 16. Now you should check this on your own using your own calculator, but you should get 0. This brings us to our second theorem, which is called the factor theorem. It says let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c is equal to 0. Okay, what this really means is that when you substitute your constant c in from the binomial x minus c, so when you substitute that constant in, if you get 0 as a result, meaning that there was a remainder of 0, it is that x minus c is a factor of f of x. Okay, so in other words, looking back to our problem number 1, we got, for problem number 1, we had f of 2, f of 2 is equal to 8. Since it's not equal to 0, x minus 2 is not a factor of f of x. So because we did not get 0 as a remainder. However, number 2, we had f of negative 4 equal to 0, which means x plus 4 is a factor of f of x. We can even take this one step further and we can actually factor it out. So we know by using the previous theorem that it is a factor, but to factor it out we actually need to do synthetic division. So we're going to take our polynomial, which was, we're going to take our constant, which was, remember, negative 4 from the binomial. Okay, and then we're going to take all of the coefficients of our polynomial. So looking at the previous problem, the first one was a 1. That was to the 6th power. Now notice here we skipped the 5th power, so that means that needs to be a 0 with a placeholder. We have a negative 16 to the 4th. We are missing our cubic, so we're going to put a placeholder in there. We do have an x squared term, and it was a 1. And then finally we have no linear term, so that's a 0 again. And then we have negative 16 as our constant. Okay, so setting up our synthetic division, we drop down the 1, multiply it by negative 4, add it, you get negative 4, multiply by negative 4, you get positive 16. This results in a 0. We have a 0 here, which is 0 here, which is 0 here, which is 1 here, then negative 4, then negative 4, then positive 16, which is 0. Okay, so again, we added vertically and multiplied diagonally. So 1 plus 0 is 1, and then multiply that by the 4 to get the new product, which is negative 4, and then you add and multiply, and it continues the pattern. So what this means, this is your remainder, this is my constant, this is my linear term, so I'm working backwards because I have so many terms. This is my x squared, but because it's 0, I'm not going to write it. This is my x cubed, again, because it's 0, I'm not going to write it. This is my x to the 4th, because it's negative 4, I am going to write it, so negative 4x to the 4th, that was a positive x. And then finally, this is my x to the 5th, so that's 1x to the 5th. All right, what that means is that this function that we wrote out previously in problem number 2 can be written as 1x to the 5th minus 4x to the 4th plus 1x minus 4 times x plus 4. And this is going to become really important when we start actually solving this. All right, so hopefully you understood that. Again, I started with the fact, I asked myself, is it a factor? And you do that using the remainder theorem that we did earlier. And yes, it was. Then I took the binomial and I factored it out using synthetic division. And then I rewrote it. So that way we have the new polynomial times that binomial. Now our last theorem, which is the number of real zeros theorem. So this simply gives us an idea of the maximum amount of real zeros that a polynomial can have. Remember, 0 is the same as solution, same as x-intercept. And then we get, from a factor, we can get the x-intercepts and the real zeros. So it says a polynomial function cannot have more real zeros than its degree. So if you simply find the degree, you can determine what the maximum number of real zeros happens to be. So in other words, looking at our first problem here, we have a degree of 7, which means 7 is the maximum number of real zeros. Max of 7 real zeros. This one, number 4, happens to have a degree of 6. And so this is a maximum of 6 real zeros.
Polynomials are my friend.